Okay, let me start the lecture today. The first 3 lectures which I prepared are more oriented on younger listeners. So the next 2 will be, if I remember correctly, on 19th and 23rd of July. I suppose make them more advanced. But this one for today is still pretty easy, pretty simple. So okay, lecture number 3, Introduction to Representation Theory. And today I will talk about very beginnings of the representation theory. So if you remember those who listened to me the last time, yesterday, then you probably remember that I ended up with the definition of representation. And today we'll start with this. So we already know, okay, those for you who know what are the root systems of Lie algebras and Verma modules probably are not really will be probably boring to hear this, but okay, let me start. So the last time I ended up with linear representations of groups. Let G be a group. Then we should distinguish somehow between the two words, presentation and representation. It's not a joke, it's really two words which you can meet in literature. So the presentation is the way how to represent your group by some generators. So it means that we choose a subset, we can choose a subset S of G such that all elements of G are products of from S and their inverses. And this means algebraically that we have an epimorphism from the free group Fs generated by S to G, which sends precisely these elements from S to the corresponding elements inside G. But now they are subject to some relations, because there are no relations in Fs except those which are imposed by the group structure. For instance, G times G inverse equals to 1. But in G, we do have many other relations in general, and I've shown the examples the last time. And the representation is a linear action of G on a vector space, or equivalently, a group morphism from G to the general linear group of the vector space, to the group of invertible linear transformations of V. Also, we can say the same words about other algebraic structures, associative, commutative, and Lie algebras. In all these cases, we also have free objects. Whenever the objects are generated by some set, there are free objects, free associative, commutative, and Lie algebras. The free associative is also called the tensor algebra. Free associative is symmetric algebra, and free Lie is free Lie, the universal invariant of which is the tensor algebra. And then also we should distinguish between the two, the presentation and the representation. Okay, this is some words from the vocabulary. Let me start with examples of group representations, and the first one is the most standard. So the group of general linear maps, the general linear group of V, the group of invertible linear maps from V to V, canonically acts on V by linear transformations, because every element from GLV is a linear transformation. Apparently, it acts on V. So whenever we have a subgroup inside GLV, then this subgroup is acting on V as well. And there are different sort of subgroups depending on the structures. If V is finite dimensional, we can define SLV, the subgroup of elements of linear transformations with the unit determinant. OV, whenever V has a positive scalar product. SOV, if the other two, the first and second, are combined. UV for a Hermitian product on V, or sometimes it's known under the name of Hilbert product. SOV is if it's finite dimensional, and so on. There's also symplectic and other choices. Suppose V and V2 are modules over G1 and G2 respectively. Then let's consider the Cartesian product, V1 cross V2, or direct product, and the direct product of G1 times G2. And then V1 cross V2 is a module over G1 times G2. So the latter is a group, again, with the product structure So if we take two pairs G1, G2, and G1 prime, G2 prime, then the product of them is a component-wise product. And the inverse is also the component-wise inverse. And the identity map is the diagonal, the identity, comma, identity. And the linear action is also component-wise. So G1, comma, G2 acts on V1, V2 as G1, V1, comma, G2, V2 for any pair of elements G1, G2, and pair of vectors V1, V2. Now let me give you, so actually the meaning of this course is not only the representation theory. I'm trying to give more concepts for younger students. And so there's a concept of product in the category, in the general category. So suppose C is a category. Suppose we have an indexed family of objects indexed by some index set I, which in general can be infinite. Then the direct product, which may not exist, is a new object X, and the notation is as for the product from for I from I capital of Xi is a new element together with morphisms, which are called projections, pi j from X to Xj for all j from I, which satisfy the next universality property. For any family of morphisms, psi I from some other object y to xi, the family is parameterized by the same index set I capital. There exists a unique morphism psi from y to x such that the following diagram is commutative. So we have all psi's to xi, the projections from x to xi, and then the combination of psi I gives you a morphism psi to x. So in general, it does not exist, but if it exists, it's unique up to canonical isomorphism. And the uniqueness follows from the property that the extension psi of psi i's is unique. You can see it, you can check it, it's just very easy to see that. Suppose there are two different x with the same property, then there is morphism from one to another one, and in the opposite direction, their combination must be the identity, again by this uniqueness. Suppose we are in the category of sets, where the objects are sets and morphisms are maps between sets. Suppose we have a family of sets xi with the index set I, where I is again possibly infinite. If it's finite, I will show that's just exactly what we know. Then the product, the direct product of sets, is the Cartesian product defined as follows. So in fact, X, which is an element of X capital, must associate to any index from I capital some element in Xi. So this is the component. And just to say this in a more precise way, it means that we have a map from X from I capital, the index set, to the union, disjoint union of OXI for OI. So the disjoint union is always defined. And the projection are what is expected to be pi j of any x is exactly x evaluated at j for all j from I capital. And for a family of maps, psi I, y to xi, the canonical unique map psi from y to x is defined as follows. So psi y sends I to the union of xi's for all I from I capital, such that psi I of I equals to psi I of y. So that's what is expected to be, and this belongs to xi, x capital I by definition of psi I, right? So and one has the property that psi I pi I applied to psi y equals to psi y j equals to psi j y, and this is precisely what we expect to be, right? So this exactly the following commutative diagram, which we have seen before. This is more or less for education, because if the product, if the family is finite, you'll see that's exactly what we expect to be the Cartesian product. So if we have a family of groups, and not just sets, but groups parameterized by some index set I and vector spaces, Vi parameterized by the same index set, then the direct or Cartesian products of Gi and Vi are a group and the vector space respectively. with the natural structure, the multiplication is determined by the property, so it's determined component-wise. So G prime sends I to Gi to G prime I for all G prime from G capital. So G and G prime are functions which associate to every element from I capital some element in Gi. And this, if you have two maps of this sort, then the product in the group gives you a new map which also associates to every I small Gi prime, which belongs to G capital I. So this is the product. One can see that this product is associative, and the associativity is induced by the associativity in all GIs for I from I capital. And the neutral element is just the map from the canonical constant map from I to the neutral element in every GI. And the inverse also is given by the component-wise inverse. So G is defined as a map from I to GI. And then G inverse is also a map from I to GI. We should simply take GI and then invert it. And then all the algebraic properties, all the compatibility properties of a group follow from the properties of GI. And for vector spaces, we do the same. Now we should know how the linear combination looks like. And the linear combination is also taken component-wise, right? So we should take the linear combination of these functions and gives you a new function. And the zero is just the identical zero. It's a constant map which sends I to zero inside VI. It's always zero. And the direct sum of vector spaces, there's a difference between the direct sum of vector spaces and the product of vector spaces, the Cartesian product. And the difference is that if this difference makes sense only if I is infinite, and then the Cartesian product may have infinitely many non-zero components. So VI can be non-zero for infinitely many i's if I is infinite. I capital is infinite, but for a vector space, we require that only finite numbers of VI's is non-zero. So for that reason, we can write this as a formal sum. So this is the difference between the direct sum and the product of vector spaces. Now, if I capital is finite, so we can order this like this. So it's just 1, 2, and so on up to n. So the number of elements in I capital is n. Then the direct product of groups is the set of n tuples. G1 and so on, Gn for Gi from Gi capital, I goes from 1 to n, with the component-wise multiplication of n tuples. And this is what is expected to be. And the component-wise inverses. And the neutral element is the diagonal element. So n tuples are in one-to-one correspondence with maps. So remember that for the infinite, in general, infinite product of sets, and in this case of groups, G was supposed to be a map from the index set to the disjoint union of groups, which associates to every index some element Gi inside Gi capital. And here we know that this element is precisely the ith component of inside the G tuple. So this in one-to-one. So well, if I is finite, then what we know is true. What we know from the school is true. If it's infinite, we should somehow take care of infiniteness. The direct product of vector spaces is under the same condition is also the set of n tuples of vectors, V1 and so on, Vn, where Vi belongs to V capital I for all I goes from 1 to n, with component-wise linear combination of n tuples, how it's written here. So C V1 and so on Vn plus C prime V1 prime and so on Vn prime is C V1 plus C, so should be C prime. C prime V1 prime, C Vn plus C prime Vn prime, this for all components. And the zero element is the diagonal element where all components are zeros. N tuples of vectors are in one-to-one correspondence with maps which associate to every element from the index set, which is finite here, the corresponding component. So V applied to I is Vi. If the index set is finite, then obviously the direct sum is the same as the product, because for the direct sum we require that only a finite number of components is non-zero, but here we have only the finite number. So the condition is always true, it's always satisfied. So in this case, the direct product is the same as the Cartesian product. Let me give you some more examples of group representations. So this is the generalization of the product of two representations. So if Vi and Gi be indexed, let these are indexed families of vector spaces, parameterized by the same index set I, such that Vi is a Gi module for all I from I capital, then let me define V tilde to be the direct product of all Vi's, is a module over G tilde, which is the direct product of all Gi's. And the representation is defined pointwise, like it was before, like for all algebraic structures, like for the group structure and vector space structure before. In particular, if I capital is a finite set of elements which we order and parameterize by numbers from 1 to n, then the representation is defined in terms of n tuples. So the n tuple G1 and so on Gn, x on V1 and so on Vn as G1 V1, comma, so on Gn Vn, where Gi is from Gi capital, Vi from Vi capital for all I from the index set. Here the index set is finite. There's some other way which we already somehow used before when we talked about subgroups of the general linear group. Suppose we have a group morphism from G1 to G2, and suppose that V is a G2 module. Then V is a G1 module either. So the action is simple. G1 applied to V the same as phi of G1 applied to V, because phi of G1 belongs to G2, and we know how G2 acts on V. It acts by some linear transformations, thanks to the fact that V is a G2 module. And there's a simple explanation. We have, first of all, we have a morphism of modules from G1, morphism of groups from G1 to G2. And second, a representation of G2 on V, which is the same in one-to-one correspondence with morphisms of groups from G2 to GLV. And now we take the composition of morphisms, first from G1 to G2, second from G2 to GLV, and we have a morphism now from G1 to GLV. And this gives a representation of G1 on V, the same we have seen before. And now the combination of previous examples. Consider the family of groups parameterized by I, such that all components are copies of the same group, probably infinite number of them, so I can be infinite. Now we take the diagonal embedding, delta I from G to the product of all G's, Gi's, but here this is the product only of I copies of G, which is defined as follows. So the image is a constant map from I to G. The image is always G inside G. So which means that actually all components are only G. So it's, given that all Gi's is G, it's also always possible to consider G as an element of Gi. If I is finite, then the diagonal is simply the n tuple if n is the number of elements in I capital, which consists only of G's. It is easy to verify that delta I is a group morphism. Thus, for this reason, V tilde, which is the direct product of Vi's, is a G module. So first we have a morphism delta I from G to the product of G's. And second, we know that this product is acting on the product of Vi's. I should say that each Vi must be a G module. So it must be a Gi module, and because every Gi is G, it's a G module. And we combine these two morphisms, first from G to the product of G's, and second from the product of G's to end morphism. So linear maps of V tilde, we obtain a structure on V tilde, a structure of a G module. Another example, which is sometimes called a regular representation, although it more refers to groups. Suppose X is a set, and F telegraphic of X is the space of k-valued functions on X for some field K. So K the elements of K are viewed as scalars. So F calligraphic of X is a vector space with respect to the pointwise addition and multiplication by scalars. It means that if you take a combination C1 F1 plus C2 F2 for any two functions F1 F2 with values in K, and C1 C2 are scalars, then the evaluation of the linear combination of functions with coefficients C1 and C2 on X is the linear combination of F1x, F2x, and C1 C2, how it's written here. Also, I did not mention here, but this is also an algebra, of course, it's commutative algebra, because we can not also only take the sum and the multiplication by constants, but also the product of pointwise product of functions. This gives us the structure of a commutative algebra. If we replace K with some other algebra, which is non-commutative in general, then we'll get again a non-commutative algebra in general. The space of vector space of functions on X, it's a linear space, it's a vector space, but it's finite dimensional only if Fx is finite. Then there is a canonical basis, the delta functions evaluated at X small from X capital, such that it's 1 evaluated at Y, it's 1 if Y coincides with X and 0 otherwise. And it's obvious that every function can be written as a linear combination of this function in the unique way. And the coefficients are precisely coefficients with respect to delta x, y is precisely the value of the function at x. So f equals to the sum of x, the sum over x from x capital, f of x, delta x. Okay, sometimes we can play the same in the infinite dimensions, but then we should either specify what are our functions or say what is the basis then. So fx is a module over the group of automorphisms of bijection of x in the following way. For every g from automorphism of x, view it as a bijection from x to x, so it's invertible map. Then we define the action on F at the composition with the inverse. So, okay, if you do not take the inverse, this is the dual map, but this we should take the inverse to make this really the action. So otherwise it will be anti-action. It will reverse the order in the product. So, and the operation respect the product in automorphism. It's easy to see that G1, G2 applied to F by definition is F composed with G1, G2 inverse. And the inverse reverses the order. So this is F composed with G2 inverse, G1 inverse. And by definition, this is the same as G1 composed, G1 applied to G2F. This is really a representation. And of course, the identity inside the group of automorphisms, the neutral element inside the group of automorphisms, which is simply the identity transformation of x as the identity on functions, because if we compose the identity with any function, you'll get the same function. So for this reason, we can say that f calligraphic of x is a module over the automorphism group of x. And it's easy to see if we check pointwise that this action is linear. Right, so we should evaluate just the linear combination G applied to the linear combination of functions on each x, and we'll see that this is really the linear combination. It respects the sum and the multiplication on scalars. So we obtain a representation of automorphism x on functions on x. If x is a G space, then there is a group morphism from G to automorphism of X. This is in one-to-one with the definition of G spaces. And if again apply the transitivity property, right? So automorphisms of X maps to the general linear group of functions on X. And here we have another morphism from G to automorphisms of X. If we compose two, we obtain a morphism from G to general linear group of functions on X, and this is the same as a representation of G on functions on X. So it means this means that functions on X is a G module. In particular, as X, we can take G itself as GG, and the product gives then, so the right G in the product G cross G to G is X, the left copy of G is G, and now we obtain a left representation of G on itself, which induces a representation of G on functions of G. And this is called, this is the name reserved for regular, it's called the left regular representation. We can do now, do the same with the right action of G on itself. So we take G1, G2, and send to G1, G2 inverse. Now in the product G cross G, the left copy of G is X, and the right copy of G is G. But now we should inverse the second component to make the action, it really to be the action. Otherwise, it will reverse the order of multiplication. It will be not an action, but anti-action. And this gives us the right regular representation of G on functions on G. Now there's another one. So the product G cross G acts on G as follows. So this is the combination of the first and the second. So the first copy of G is acting on G by the left multiplication, and the second copy by the inverse of the right multiplication. And this gives an action of G cross G on G, which implies that functions on G is a G cross G module. Now, if you look at the diagonal embedding, we do the same trick as before. So we take the diagonal embedding, G inside G cross G, and now we know that G cross G is acting on functions on G. This means that if you combine both two, take the composition, it means that functions on X, functions on G should be a G module. And this is the third way how to endow G with a structure of a G space and functions on G with a structure of a G module. So there's something in chat, right? Can someone share a link to the already uploaded lectures? There's, I guess this is on the web page of the conference. At least, if I remember correctly, my first lecture was already shared. Maybe the second one is either shared. I don't know. I don't remember. Okay, now submodules of a G module. So we know what are the modules. So there should be some something again. Yeah. Okay. Yes. Precisely. This is the link to the program and everything. If it's somewhere, I'm sure that the link will be on the homepage of the conference or of the school. Okay. Submodules of a G module. Suppose G is a group, and V is a module over group, and let us and assume that we have a vector subspace W inside V. Then W is called a G submodule of V if it's closed under the action of G. It means that if you take some element G small in G capital and W small in W capital, then G applied to W small is again in W capital. This means that the W is stable under the action or stable or closed with respect to the action of G on V. The zero subspace of V is always stable under the action of G because G is acting by linear transformations, although non-degenerate, but still, and we know that for any linear transformation, there is at least one fixed point, the zero. And V itself is a submodule because, because G is acting on V. But they are not interested in submodules, they are trivial submodules, of course. And the representation is called irreducible, and the module is called simple if there are no other submodules. So if there is any submodule W of V, then W is either 0 or V itself. Otherwise, the representation is called reducible. In fact, the desired task in the representation theory is to find all irreducible representations. And then if we are lucky enough, for instance, if the group is finite or simple or compact, then we are able to decompose each representation into the direct sum, or should we also care about the representations? But if they're finite dimensions, always true. If infinite dimensional, we should use some topological properties. But our desired task is to be able to decompose every module into the direct sum of irreducible modules. And later I will show that this decomposition is very unique, and this will follow from the Schur lemma. I will not tell this today. I will prove the Schur lemma and show it, but this will be the subject of the next lectures. So suppose we have a submodule W inside V, then the quotient space V divided by W is again a module over G. How the quotient space is defined? So first of all, well, it's known, but I know that it's not always defined in courses of linear algebra in the basic course. Sometimes it's missed. So let me repeat what it is, at least for the first and second classes. So first of all, we have a vector space and a vector subspace W inside V. Then we impose the following relation. So V1 is related to V2 if V2 is obtained from V1 by shift of some vector W small from W capital. So I write it as follows. So V is always equivalent to V plus W small for all W small from W capital. Then you can show that this is an equivalence relation. So this is reflexive, transitive, and symmetric. So V, of course, is equivalent to itself. We should take W equals to 0. If, yeah, something in the chat. Okay. Probably someone already found the lectures on the homepage. So if V1 is equivalent to V2, then V2 will be equivalent to V1 with minus W, and the transitivity will be obtained by adding of two different W's. So this really an equivalence relation. We can take the quotient, the set of equivalence classes, and this set of equivalence classes will be endowed with the structure of a vector space. Actually, we already talked about the quotient of an abelian of a group by a normal subgroup, and this is a particular case because V is a abelian group with respect to the sum. W is a normal subgroup because the structures are abelian, but in addition, this is also closed under the multiplication of constants. So this is really a well-defined vector space. V over W is not only an abelian group, but also a vector space. And provided V and W are a G module and a G submodule, respectively, then the quotient V by W is a G module itself. Okay, so now whenever we know some objects, algebraic structures like groups, algebras, fields, whatever, everything, or modules, how it's here, then we should also know what are morphisms between them. Then we'll be able to construct a category. And in fact, for instance, algebraic topology is about morphisms from functors from the category of topological spaces, or the homotopy category of topological space up to homotopies, to some category of algebraic structures. So this is the way how, for instance, cohomology are defined and whatever, cobordisms, many other things. So morphism of modules. Suppose a linear map phi from V1 to V2, where V1 and V2 are G modules. It's called a morphism of modules if it commutes with the G action. So phi applied to GV equals to G phi of V for all G from G capital, V from V capital. A morphism of modules is a monomorphism or epimorphism or an isomorphism if the corresponding linear map is injective. So the kernel is 0, surjective, the image coincides with the whole codomain of the target, and bijective is if it's in one-to-one, respectively. Okay, now examples of submodules, which is very important. We'll use this later while proving the Schur diagram, Schur lemma. So the kernel and the image of phi are G submodules. Also, the composition of two morphisms of G modules. if it's defined, so if the source of one is the target of another one, is a morphism of modules. And the identity map from V to V is a morphism of modules. Of course, by definition, it must commute with the action of G. It commutes with everything. And the inverse of any morphism is again a linear map. It's a linear map again. If it's invertible, it's a linear map. It's invertible linear map, but it's also a morphism of G modules. So the inverse of any morphism, if it exists, is an invertible morphism. And all G modules together with their morphisms is a category under the composition. So the objects of this category are modules over G, and the morphisms are morphisms of modules. So let me give you more examples of submodules and morphisms. For each submodule W of V, the inclusion of W inside V and the quotient map from V to V divided by W, V over W, is a monomorphism or an epimorphism of modules respectively. The first one is, of course, a monomorphism because W is included inside V. Of course, if some element is in the kernel, it means that this element must be zero because it's zero inside V and the whole W is inside V. And this is an epimorphism. So the next map is an epimorphism. It's on2 simply because every class, which is an element in V divided by W, can be represented by some element in V capital. So it's indeed an epimorphism. A vector space over a field K is a K star module where K star K is a field and K star is the group of non-zero elements in a field. Just remember that a field is a ring where all non-zero elements are invertible. So K star, which is the set of all non-zero elements, is a group inside K. And then whenever we have a vector space, the set of scalars is acting on this vector space by definition. So it means that some particular non-zero scalars are also acting. So it's a K star module. So but now there's a huge possibility of choosing submodules because any vector subspace is a submodule and any linear map is a morphism of modules because a linear map by definition commutes with the field K, and for that reason commutes with K star because K star inside K. For a G module V, the subspace of linear functions. So we can take, so suppose V is a vector space, G is acting on V. Then if we view V as a set, we know that functions on a set, it meets a structure of a G module. But now we can take, now we know that G is acting linearly on V. We can take linear functions, linear scalar functions from V to K, and then given that the action of G is linear, the composition of two linear maps is again linear, it means that G preserves the subspace of linear functions, which means that V star is again a G module, and this is called a dual module. If X is topological space, we can play the same game. If X, the set, it has some structures, we can look at functions which respect the structures, for instance, differentiable functions, continuous functions, smooth functions, complex analytic functions, algebraic functions, and so on, whatever we have. And if G respects the structure, then G is acting on this particular subspace of functions, actually usually normally subalgebra. So in particular, if X is a topological space, or X is a smooth manifold, and G acts by continuous or smooth mass respectively, then the subspace of continuous or smooth infinitely many times differentiable functions on X is a G submodule. As I said before, instead of smooth functions, we can take analytic functions or algebraic functions depending on the structure on X, if G preserves this structure. Well, and if we come back to the products, suppose we have a family of modules, Vi over Gi parameterized by the index set I capital, then the action of the product of groups G tilde preserves, so it, as we have seen before, it acts on the product of all Vi's, but it also preserves the direct sum, which is here the subspace of elements in the Cartesian product, such that only a finite number of components is non-zero. And it's obvious that GI will preserve this because if some element is 0, if you apply a linear map to this element, it will become 0. So if it was finite number, it will be again finite on the same positions. So it means that the direct sum is a submodule. There is a simple naive representation. Suppose we have an arbitrary group G capital and an arbitrary vector space. Then there exists at least one representation of G capital and V, which associates to every element G small and G capital the identity map. And the identity map, this constant map, of course, will respect the structure. For algebras, this must be the 0 map. For groups, it must be the identity. Of course, it will set the neutral element to the identity because it sends everything to the identity. And the product will be sent to the product because the product of identity is again identity. So it's the childish example, which is, by the way, good because for any G module, we can define the set of invariants. It's a very important task in algebra and geometry to find invariants. And if we have a representation of G and V, then let's consider the subspace of invariants. We can show that this is vector subspace, of course, in easy way. So this set of vectors V from V capital such that GV equals to V. So this is not only the subspace preserved by G, but every element is. And this is a G submodule because, and this is also a trivial module itself because every G acts as the identity map. So that's a simple example. So let's consider the following action of U1, so the unitary group. So this U1 is the unitary group. It's the group of unitary linear transformations of C2 with the so by definition the absolute value of so they're given by multiplication of some non-zero complex number, and by the property that this preserve the Hermitian product, it means that the absolute value of this number is 1. So which means that U1 is in one-to-one correspondence with complex numbers with the unit absolute value. And this is the same as S1, which is parameterized by angles theta. So which means that every element in U1 can be written the exponential of I theta, where I the complex unit. And that's write the following action on R3 with coordinates x, y, z, which sends x, y, z to, actually it rotates the first two coordinates, but the last one, the third one remains unchanged. And for that reason, the set of elements 0, 0, z for all possible z's is a submodule of invariant vectors because there are no submodules. If it was only R2 with the first two components, then the only invariant vector wouldn't be the 0 vector. But here there's some auxiliary component, and then the invariant subspace is one-dimensional. Now let me, so I gave many examples, at least let me prove at least some theory. So there's the Schur's lemma, which consists of two parts. I will prove both parts, so we show both parts, but they will be somehow separated. So after the first part, I will show examples, and after the second part, I will also show examples. Suppose V1 and V2 are two finite dimensional reducible representations of a group G, and phi is a morphism of modules from V1 capital to V2 that commutes with the action of the group. We call morphisms of modules. That's another notation for them. We call also G linear maps or linear maps over G. That's the same. Then phi must be either invertible, then it's an isomorphism, or trivial 0. There are no non-trivial different from an isomorphism and the trivial map. Morphisms from V1 to V2, where V1 and V2 are irreducible representations. In particular, if V1 and V2 are not isomorphic, then the only 0 is possible. Well, the proof is very simple. It's based upon the fact that the modules are simple. It means there are no strict submodules which are different from 0 and the module itself. And second, the kernel and the image of any morphism is a submodule. right? Let's take phi morphism from V1 capital to V2. Consider the image of phi. It must be submodule inside V2. So there are actually two options. So first, the image of phi is 0 because it's a submodule inside V2. It can be only either 0 or the whole V2. So the first option, the image is 0. Then, of course, phi must be 0 because it sends every element to 0 inside V2 capital. And the second possibility, the image is V2 itself. Then, okay, we should assume that V1 and V2 are finite dimensional, but not 0 spaces. At least the dimension at least 1. Then, if the image coincides with V2, the whole V2, it cannot be a 0 map, which means that the kernel of phi cannot be the whole V1. So this means that it must be 0. And if the kernel of phi is 0 and the image coincides V2, it's a bijective linear map. So phi is an isomorphism of the modulus. If kernel of phi is 0, it's an injection or monomorphism, a linear monomorphism, or monomorphism of modulus. If the image coincides with the whole target, then it's an epimorphism. And monomorphism and epimorphism in the finite dimensional case is an isomorphism. So it's a bijection. So let me give you an example. I will actually this example quite instructive. It's maybe one of the, of course, many of you know this, but at least for younger students, it's a very instructive example. So first of all, let me use the following notations. This for the for this and the end of this lecture and the next two. So I write homomorphisms over G, the index subscript G. This is the set of morphisms from V1 to V2, homomorphisms over G. And if V1 coincides with V2, then homomorphisms over G from V to V is the endomorphisms over G from V. This is just the notations, the names. And the first is called homomorphisms, the second endomorphisms. Now let us consider the algebra of quaternions. So you know that the algebra of field of complex numbers, viewed as an algebra over real numbers, is spanned by the identity and the complex unit. And the complex unit is the subject to the relation, if you call this I, is subject to the relation I squares to minus 1. And then this gives you the unique up to an isomorphism algebra with division, which is commutative, and this is C over R. The complex numbers viewed as an algebra over R. H is again an algebra over R. The basis is 1 I j k. Now we have 3 complex units. All 3 satisfy the same property as the first I squares equals to j square equals to k square equals to minus 1. They must anti-commute. So ij equals to minus ji, ik minus ki, and jk minus kj. And there's an additional property, ijk equals to minus 1. So actually from the last property, we see what is ij, right? If you multiply the right-hand side, the left-hand side with k, we'll get on the left-hand side ij times k square, which is minus 1, so minus ij. And the right-hand side minus k, which means that ij equals to k. So by the same trick, we can get jk equals to I and ki equals to j. But instead of writing these 3, let me write the first, just ijk equals to minus 1. The multiplication of quaternions is obtained by extending the multiplication on generators by bilinearity to the whole H. So if you have a linear combination of vectors, one vector is a linear combination of one ijk and the second one is the same, then we just open the brackets and develop the brackets and took the all possible products. And this will be gain, given that the multiplication of generators is again one of the generators, this will be gain of the same form. So it will be spanned by the same basis, 1 ijk. Also, given a quaternion, let's define the real imaginary part of x. So the real part of x is x0, so which corresponds to the identity. And the imaginary part is what remains. So x1i plus x2j plus x3k. And the conjugate, Now, the conjugate for a complex number x0 minus x1 plus x1i will be x0 minus x1i. But now we should conjugate with respect to all three complex units. So we should put minus for all three components but x0. So the complex conjugate will be an anti-involution. So the conjugate of xy will be the product of y conjugate x conjugate for all pairs of quaternions, and the absolute value. Let's define the absolute value. The absolute value will be just the scalar product in the quaternions viewed as a four-dimensional real vector space, just the sum of the squares from 0 to 3, so therefore. Then you can easily see that for any non-zero x, x inverse can be written in terms of the conjugate and the absolute value. So it's easy to see that the absolute value is 0 if and only if x is 0, simply because the scalar product is positive definite. So it means that if x is non-zero, the right-hand side is well defined. And now you can see that just by the definition that the absolute value is qx to x prime. If you multiply the right-hand side with x, you'll get x bar x divided by x squared, but the x bar x is precisely the absolute value x squared. So we'll get 1. H is non-commutative, but if you take only the real value, it will commute. So under the real value linear functional, it will commute for any two quaternions x, y. Also, the absolute value, so it gives us the structure of C star algebra. So the absolute value of x, y equals to the product x, absolute value x and y, and the absolute value of 1 is 1. Therefore, if you consider the set of all quaternions with the unit length, so the quaternions such that x such that the absolute value of x equals to y, they will be first non-zero, so invertible. Second, the product of these two quaternions will also have the absolute value equals to 1. So it means that they are closed under the multiplication and taken the inverses inside the group of non-zero quaternions, and this is called SP1. This is a group of unitary quaternions. In fact, it's easy to understand what is the dimension of this group, because so the dimension of H over R is 4. The dimension of H star is again 4 because we extract a subset of measure 0. Then now we impose one condition. Actually, the sum of the squares of components equals to 1. So in fact, the dimension will be 3, and the SP1 will be the same as S3, the three-dimensional sphere, because the condition, the absolute value x equals to 1 is the sum of the squares of the components equals to 1. That's the equation for the sphere. SP1 acts on H on the left by orthogonal transformations, and from the above properties, we see that the norm will be preserved. This endows R4 with the structure of SP1 module. Now we can do the following trick. We can view H, the quaternion, the space algebra of quaternions, as a complex vector space. So of course, it's always a real vector space, a real four-dimensional vector space. But we can also multiply H by complex numbers, and we see complex numbers inside H as those quaternions for which the third and the fourth components are zeros. This will satisfy the property of a complex number. And now the algebra of quaternions is not commutative, but the multiplication on the left-hand side and right-hand side always commute. So which means that the action of quaternions on the left will commute with the action of C on the right. The action of C on the right gives us the structure of a complex vector space on H, and this complex vector space will be now two-dimensional. So if it's four-dimensional with respect to real numbers, it's two-dimensional with respect to complex numbers. And now SP1 becomes even a complex subgroup of GL2C. So, and the second and the third properties imply that SP1 inside the unitary group of C2. And in fact, this coincides with the subgroup of unitary operators with the determinant equals to 1. So that's an explanation of this fact, simple explanation of this fact, which is useful because, in fact, in mathematics, sometimes it's good to define something over the algebraically closed field. For instance, we know that C, the complex numbers, is an algebraically closed field, and then view real numbers as complex, real spaces as complex spaces with some additional structure. Now, in general, let us define the scalar product, which is positive, the scalar product f x and y as the real part of x bar, the conjugate of x, y, for every pair of vectors x, y, and h, capital. And this extends the norm of x, because if you substitute y equals to x, we'll precisely obtain the square of the norm. Because then x bar x will be just x square, and the absolute value x square, and the real part of it will be the same, the absolute value of x square. So it means if you substitute y equals to x, we'll get the norm of x square. Otherwise, it's a scalar product which is positive. It's easy to see. Then, okay, someone said that the internet connection is unstable. Do you hear me?
Yes.
Yeah. Okay. Nice. I don't know. I hope you'll be able to finish it at least. So this makes. Yes. Good. Great. Okay. So this makes H into a Euclidean vector space. It's a real vector space here, four-dimensional, with a positive norm. Again, yes. Yeah. I believe now it's true. Then the right action by the imaginary quaternions is skew joint with respect to this scalar product. So for any z from H with the real value, real part of z equals to 0, we also have the conjugate of z equals to minus z in this case, and one can easily see that x, if you act on y in the scalar product on the right by z, then using this simple transformation, we'll see that the same is minus x z y. So it means that z is skew joint or skew symmetric with respect to the scalar product. So whenever we have a complex vector space together with a real scalar product, when we view a complex vector space as a real vector space, then it's Hermitian if the multiplication of the complex unit is skew joint, as I said before. So the correspondent symmetry, Hermitian product or Hilbert product can be obtained. So the product which is now not real valued but complex valued with this skew symmetric property that V1 V2 equals to the conjugate of V2 V1. It's defined as follows. So this product is the real part of it is 1 V1 V2, and the imaginary part is I V1 V2. So whenever we have a real vector space with a scalar product, together with an action of I of a complex unit, which is skew symmetric, skew joint, then we immediately have a Hermitian product on this vector space, which is now viewed as complex because we have an action of a complex unit. This was an explanation of the above, that the unit quaternions are acting as unitary transformations. On the other hand, suppose we take a non-zero quaternion and y an arbitrary quaternion, then the real part of x, y, x inverse is the same as the real part of x inverse x, y, which is the same as the real part of y. So for that reason, the subspace of imaginary quaternions for the real part equals to 0 is stable under the action of H star. And this contains only 3 components, so it's isomorphic to R3. We can induce the scalar product from the scalar product in R4. The conjugation will also preserve this. And thus R3 is a SP1 submodule of H inside R4. It's a module of H. So we have a group morphism from SP1 to O3 to orthogonal transformations. In fact, it will take very soon as O3. It induces an epimorphism from SP1 to SO3. The kernel of which is plus minus 1. So before we have an embedding of SP1 into U2, and the image was SU2, and now we have an epimorphism with a finite kernel. So apparently these two modules, R3 and C2 and R4, cannot be the same. They have different dimensions, but in both cases they are reducible. You can see that there are no submodules other than the 0 and the whole module. So we obtain two representations of SP1. They are different, of different dimensions. Both are reducible, and there are no SP1 linear maps between them, except the trivial one, 0. Because they are not isomorphic, the isomorphism is not possible. Then by the Schur's lemma, the only possibility is 0. And now the part 2. I'm close to finishing now, maybe 1 or 2 minutes. So this is the part 2 of the Schur's lemma. Suppose V1 equals to V2, and V is a reducible finite dimensional G module over an algebraically closed field, and phi is the linear map from V to V, linear endomorphism over G. Then phi can be only a scalar multiplication on some scalar. So it's a scalar multiple of the identity. The proof is just again very simple. So if K is algebraically closed, so for instance K equals to C, we can always find an eigenvector which is not 0, which means with respect to some eigenvalues lambda, which means that the set of vectors, eigenvectors, lambda eigenvectors is not 0. Then we can easily see that this subspace inside V must be a G submodule, simply by the reason that phi commutes with G. If V was a eigenvector, phi eigenvector with the eigenvalue lambda, then so is GV. Therefore, V lambda is not 0 because there's at least one non-zero eigenvector. Then V lambda must coincide with V because V is a simple module. It means that phi is always acting as multiplication of lambda. All vectors are eigenvectors with the same eigenvalue. But if K is a more general field, then the space of G linear endomorphisms is only an algebra over K with division. And for K equals to R, there are 3 possibilities. There are only 3 division algebras over R, C, and H. The first 2 are commutative. The second one is non-commutative, but it's still a division algebra. And all 3 can be easily obtained from by the Schur's lemma. So, for instance, the simplest way is how to obtain. The first one, G is J and R, and there's a canonical representation on columns with all elements from R. Then all endomorphisms, all linear maps commuting with GLN, by definition, only multiplication of constants. So it's R. So if you take G and C with the canonical representation on Cn, where Cn is viewed as R to N, then endomorphisms will be C by the same reason. And now if you take G equals to G ln H, where H is quaternions, so this is a group of invertible matrices whose entries are quaternions, it's still a group. Then it acts in the standard way on columns whose entries are elements on H. But on the other hand, H is acting on the right on the same columns. And this action on the right gives all endomorphisms over G of Hn. And we obtain H now. So using the Schur's lemma for A equals to R, we can obtain, as particular examples, all possible division algebras, R, C, and H. Okay, so this is all what I wanted to say today. So if you have questions, just ask me. But I think it was pretty easy, right? Yeah, of course there are. Well, so for a general action, there's a question for a general action instead of representation. Yes, for a general action, we can talk about invariant subspaces. Of course, it's not clear what is the quotient. We can still talk about morphisms, which are maps between 2 G spaces commuting with the G actions. So there are a lot of similar things, except that if some additional structure next, like a vector space structure, it's an abelian group, or it's an algebra, then we should specify what kind of morphisms can be taken, right? So there should be morphisms respecting these additional structures, of course. Okay, so if there are no more questions, let me stop the recording now.